It's really tempting for me to say something like, you'll find this chapter easier. It scares me to say stuff like that. Because what's supposed to happen now, and what often happens in 11U, is from here on in, people do way better. Like way better. There's supposed to be two things that happen at once. One is your work approach, we'll call it work approach, has gotten way better. Due to fear, maybe, of the first 4 chapters. And second, the work gets a little more straightforward. Because we're introducing some new stuff, and whenever we introduce some new stuff, things automatically get a little easier. Yeah? But when I say that, then people relax. They go, oh, this is going to be easier. Then they stop working, and then they don't get the payoff of their newfound work approach. So let me just say it aloud. If you keep the work approach you've been learning lately on these new chapters, you might see some very dramatic results, like some very shockingly high marks on this stuff. I think you'll see in today's lesson, you're going to be like, so that's it? When I wrap it up, you're like, so that's it? Oh, that's pretty good. But see, when that happens, I know what people think. They're like, oh, it's an easy lesson. I won't bother doing the homework. Horrifying thought process when you do that. You're like, I really get this stuff. I'm going to do the homework, so I do great on this. Okay? Anyways, here it comes. This is called comparing linear, quadratic, and exponential functions. I'm going to teach this as if you haven't had much time to do the investigation. Okay? The investigation / assignment. That's how I'm going to teach it. All right? So if you have done that, you might be a little bored with some of the things I'm going to say here. Identify the following functions as linear, quadratic, or exponential. Personally, I don't do these questions in order. That is not how I handle questions like this. I look through and go, do I know what linear is? And it should look like something like y equals mx plus b, and I just go out and pick those ones off. And what y equals mx plus b means is you'll see y's, you'll see x's, but you won't see any squareds or exponents or anything. Just bare bones stuff from grade 9. Who's got one? Who can pick one off? Which ones of these is linear? I think I see 2 of them. Yeah, this is the classic linear one. This is the one that you learned about the most. Crazy fraction and then a nice y-intercept. Like, so fractions are okay? Yeah, it's y equals mx plus b. Y's, x's, totally allowed, and it's going to be linear. It's going to be a line, as long as there's no exponents in anything. So this one qualifies as well. Y equals 2x. That's also linear. Yeah, it doesn't have a b. Well, I could be sarcastic. I could say, yeah, it does. I could say, yeah. The b just happens to be 0, so we don't write it there, okay? But moreover, I want to stick to what I was saying, is if you're looking for a linear function, you're looking for y's and x's only, no exponents.
The representative from the University of Toronto is here. Students who have previously signed up in student services are asked to go to the Divine Mercy Room now. Thank you.
Someone raises their hand and goes, well, actually, that does have an exponent. It's exponent 1. I'm like, okay, you know what I mean. It doesn't have an exponent like a 2 or a 3 or something like that. Okay. Next, quadratics. You saw it in grade 10, and then we just beat you up with it last chapter. The idea is, in a quadratic, you could see, you could see standard form, like that. You could see vertex form. Or you could see factored form. How are we going to recognize it? Well, the simplest way to recognize quadratics is that there could be a squared here. That's all I'm looking for. Something that's got a squared in it, or could have a squared in it if I multiplied out the brackets. I see several. What's the obvious one? Actually, I haven't shown it. So, yeah, this is the standard form. Yeah, so this is a quadratic. Well, you can see the squared, right? But it's in vertex form. So by the end of the chapter, those were supposed to be 2 forms that were like starting to get familiar, where you're like, okay, I kind of have a handle on this. Standard form, standard form, vertex form, starting to get a feel for that. Now, if I didn't know what I was doing, I'd just call the rest exponential and say, I guess they must be exponential. But I'm here today. This is the one of the 2 or 3 things big I want to show you today. When we say an exponential function, they look like this. And you don't have to worry about the A's, B's, and C's. You're like, oh, here we go with the A's, B's, and C's. None of that matters. I'm going to change colors and really get to the point about this. The x is the exponent. That's why it's called exponential. You really want that there. That's what's different. See, because this one here, 2 to the x, looks a lot like x squared. What's the difference between the 2 of them? One of them is x squared, and one of them has x as the exponent, which the investigation is supposed to get you used to what happens when you run into x in the exponent. So this is exponential. And for you, it's as simple as if the x is in the exponent, we're talking about exponentials. What do those look like? Well, we don't know yet. All we got is a name for it right now, unless you've worked on the investigation, and then you're getting a feel for what exponential look like. And I'm going to talk about that more as the class goes on. So what other ones have x as the exponent? This one, the really complicated looking, but that's not what we're doing, but the x is up in the exponent. Yeah, we're going to deal with all this complicated stuff eventually in the chapter, but for now, we just know the x is up in the exponent, so that's an exponential. And this one, down here, because it's got an x up in the exponent. So that's a great definition. I'm not taking credit for it. I'm just telling you, once you have that in your toolbox, that the x is the exponent. So I'll go up there and highlight that too. Because if you're really like taking my word for it, going, this chapter can be way better. What happened there? Oh, I'm in eraser mode, highlighter mode. You're like, I want this chapter to go better. Things like this really help to highlight these things and put them on a separate study page. How do I know an exponential? An x in the exponent. Oh, I missed one. It's going to look like I did that on purpose. I didn't. I just forgot about it. Which type is this? Is it linear? No, because it doesn't have just x's. Quadratic. It's a quadratic because it's got x squared, not the x in the exponent. See, quadratics were easy to recognize a few minutes ago. Now with exponential in there, you got to think just a little bit. You know, this happens in math where something easy becomes a little bit difficult because I've added something to it. Any questions about that? Do you need more time? If we are given a table of values, how can we tell if a linear relationship exists? You were supposed to learn this in grade 9, but I get it. This information can slide away on you, and I'm going to use it in just a second. So if I write the sentence and you remember it, great. If you don't remember it and don't know how to do it, it's okay. That's what I'm going to do in the next part of the lesson. If we are given a table of values, how can we tell if a linear relationship exists? What's that? If it's a consistent increase or decrease. Absolutely, that is exactly right. And this is the fancy way I'm going to write it, not to mess you up, but to get ready for other examples, okay? So the first differences are equal, but I'm going to add his sentences to that so you don't get messed up by my fancy words. How did you say it, Nathan?
Consistent increase or decrease.
Consistent increase or decrease. That's the ultimate definition of linear. It's got to go up in a straight line. It's got to go up by the same amount all the time. That's what grade 9 was all about. Things that go up by the same amount every time. Now, if we were given a table of values, how can we tell if a quadratic relationship exists? One part lesson in grade 10. Yeah, do you see what I set up here by calling it first differences, then the second differences? It was one part lesson in grade 10, but maybe it stuck. Maybe it stuck in there. If it's quadratic, the second differences will be equal. And do not panic. Just copy it down for now. And if you're like, I don't even know what a first difference is, let alone a second difference, I don't know what's happening, I'm lost, I'm in trouble. No, hold on. Wait till I do first and second differences. I don't think you'll find them particularly difficult to find. Where am I headed with this is to find out what happens with exponential. I did linear, I did quadratic. Now, what's exponential? It's not third differences. There's third differences out there, but that would be for something that was x cubed or x to the fourth. All right, push that off to advanced functions. We do that exact thing in advanced functions. I do the exact same sequence, and then I go, what about exponent 3? Third differences. What about exponent 4? Okay, so we'll do that in a different lesson. Not harder, just different lesson. Now it's what happens in an exponential function. And now I'm going to do part of your investigation for you. This is what you do in the investigation is you go, okay, make a table of i's for 2 to the x and find out what the heck is going on with this thing. So you go 2 to the 0, which is 1. You do 2 to the 1, which is 2. 2 to the 2, which is 4. 2 to the 3, which is 8. 2 to the 4, which is 16. And 2 to the 5, which is 32. Now, I built that a million times in my life, so I can just pick them off like that. On the investigation, you just hammer them into your calculator. That's fine. That's a great investigation, is to find out what is going on with exponentials. And we're supposed to, by the end of this, look at what the sentence says. If we're given a table of values, how can we tell if it's exponential? We're supposed to be able to look at the y values and be able to tell that's exponential. You might not be able to right now, but by the time I do 3 in a row, maybe we'll see what's happening. So I'm going to do it again for 3 to the x. I forget if your investigation does 2 to the x and 3 to the x. It does all sorts of things to the x and just keeps playing around with them so you can get to know what it is. So a lot of your assignment / investigation is just plugging into these things, going 3 to the 0, punch in, you get 1. 3 to the 1, I don't need a calculator for that one, that's 3. 3 squared, maybe I don't need a calculator for that one, it's 9. But maybe by the time you get to 3, you're like, I better punch these in. 3 to the 5, 243. Well, now we need someone clever. I'm going to do the third table in just a second, but the third table is just a little tiny bit different. So I want to focus on these first 2 tables first and get a hypothesis going about what happens in these table of values. And I'm going to write this, and hopefully that triggers your memory about first and second differences. If it doesn't, that's okay. I'm going to do some examples in just a second. At least my brain tells me I'm going to. Let me flip the sheet over. Oh yeah, in a second I'm just going to do all sorts of first and second differences and play around with it. But this is the way first and second differences work. If this was first differences, I just subtract to see what it was going up by, to find out if it was a consistent amount it was going up by. But it's not a consistent amount. Look, it goes up by 1, then 2, then 4, then 8, then 16. It goes up by all sorts of different things. But what does happen in the table of values? If I go from 1 to 2, and then from 2 to 4, and then from 4 to 8, what's happening in the table? It's doubling. Is that, were you going to use the word doubling, or were you going to say something else? Multiply by 2. Same thing, okay? So these are actually called first ratios instead of first differences. So over here, I'm going to write down the first ratios. And you're like, why are you breaking out these crazy words when we had it under control? You know, it was doubling. Yeah? I'm like, yeah, same thing. First ratios means 2 divided by 1 was 2. That is, if I take 2 and divide it by 1, it doubled. It multiplied by 2. You're like, again with the fancy words. Why are you making it so weird looking? Well, maybe it won't be 2. Maybe it won't be 3 nicely. Maybe it'll be 1.7 every time. So I'm trying to get ready for tougher numbers here. But see, it happens all the way along. 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. 32 divided by 16 is 2. Mr. Todd, do I have to write them all if I can see it works? No. My job is to get you ready for tougher examples. If there are a whole bunch of crazy decimals, you're going to have to do every single one to make sure it's exponential. Does it happen here? Are these first ratios the same? What's it multiplying by every time here? 3. And actually breaks through a major league result about exponentials. Not complicated, but 2 to the x means something's doubling. 3 to the x means something's tripling. Yeah? It's not a mind-blowing detail. It's just something you got to know about here. So if you can see what it's multiplying by, yes, you can just write that for first ratios. But please don't forget about this, dividing them to figure out what it's multiplying by if the numbers get a little bit complicated. We got a theory going here about how we'll know if something is exponential. Let's do it with a fraction. Let's see, 1/2 to the 0 is 1. Well, anything to the 0 is 1. 1/2 to the 1 is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8. I'm trying to say them out loud just in case this is too small to read. 1/2 to the 4th is 1/16, and 1/2 to the 5th is 1/32. Does it work there? Is there something that is multiplying every time? Like when you go from 1 to 1/2, what are you multiplying by? Is it the same thing that when you multiply, when you go from 1/2 to 1/4? 0.5, yeah. I'm going to write 1/2. 0.5 would not be wrong. I'm just trying to keep that balance going between fractions and decimals. So I'll call this again first ratios. It's what did I multiply by every time? Why is it called a ratio? Because sometimes you're going to have to divide to figure out what was multiplied by. And I'm ready to make my final statement here. How can you tell if an exponential relationship exists? The first ratios are equal. And in a minute, I'm going to practice all those three things a bunch of times. And then I got one last thing to show you, and that's it for the day. Is this Wednesday? Stay Wednesday? What questions do you have about that? Do you need more time? All right. Let's practice this out. It says, your next thing just gives you a bunch of tables and says, decide if they're linear, quadratic, or exponential. Some versions of this question also say, or none of those. So we don't mean to imply that everything in the world is linear, quadratic, or exponential. That's not true at all. This one doesn't ask that, so I presume that means these tables have been set up that they're one of the three. Well, I don't do these in order, I must tell you. I like to poach questions. I'm going to go find a linear one. Can anyone find a linear one? Ben. The very first one, he can look at it and tell. And if they're nice numbers, you can just tell by looking at it. I'll do the first differences as I speak about it so you can see why they're called first differences. See, when you go from 5 to 8, 8 minus 5 is 3. You're like, I don't need to go 8 minus 5. Why are you making it more difficult? In case the numbers get crazy. Sometimes you'll have to subtract to figure out what was added. But it happens everywhere all the way along, right? 11 minus 8 is 3. 14 minus 11 is 3. 17 minus 14 is 3. 20 minus 17 is 3. All the way along, it's linear. See, I like poaching these questions, me personally. Do them in order. You can do that too, but what else? She says the next one's exponential. Did you do the second differences, or can you tell by looking at it? Did you do the second difference? Oh, exponential, right? She looked at it and said, I can see it's multiplied by 2. See, the poaching method's good. I just happened to be the first and second one, but they might be all jumbled up, and the easy ones might be down here somewhere. So you just look at them and go, okay, well, she can see that, and I'm going to write the first ratios this time. 6 divided by 3 is 2. That was multiplied by 2, and you probably didn't have to divide to figure out that it was multiplied by 2, but maybe you run into one where it's like it's multiplied by 1.7, and then you got to divide to figure it out. Okay. 12 divided by 6 is 2. 24 divided by 12 is 2. 48 divided by 24 is 2. Mr. Todd, do I have to do them all once I see the pattern? The world answer is yes. It could stop being exponential at some point. The grade 11 answer is probably no. Once it works, it probably works all the way through. We're not trying to fool you necessarily. So exponential. You know what? I think I misheard you. I thought you said quadratic, and then you didn't say that. You said exponential. Right? So that's why I was wondering how you knew. All right, we're off to a running start. I got 2 of them already. Let's go the other way. Let's pretend you're not a poacher. How would you approach this if just a random table comes up and you look at it and you don't know which one it is? I just do them in order. I try first differences. I go, okay, up by 1, up by 3, up by 5, up by 7, up by 9. I check the first differences, and if you didn't know what second differences were, they're the differences of the differences. And you go, okay, well, from 1 to 3 it goes up by 2. From 3 to 5 it goes up by 2. From 5 to 7 it goes up by 2. And from 7 to 9 it goes up by 2. That's the second differences, so that's quadratic. You advanced functions people, yes, we will do third differences and find out, oh, those are cubic exponent 3's. We'll do a little bit of that.
So if we ever have to use second differences, it's automatically quadratic?
No. This could also not work. It wouldn't have worked here on the exponential one. So you do the first differences, didn't work. Try the second differences, didn't work. Then try the first ratios and divide them and see if that works. And it looks like I got to go all the way through? Usually not. It would have failed early. It wouldn't have taken long before you're like, it's not second differences. Like, so you don't have to go as far as you think you have to. I'll act like I don't know what's happening, but most times you'll be able to see what's coming. Yeah? For instance, let's do this one. Let's pretend you went through and said, okay, is it first differences? Negative 200, negative 100, negative 50. No, it's not first differences. So then you go, okay, well, let's try the second differences then. That's positive 100. That's positive 50. It's not the second differences. See, I didn't have to go all the way through the table to know it wasn't going to be first and second differences. Is it ratios then? And this won't play well on my completed version of this note because I'm erasing all that. Now I'm going to go, okay, what do you multiply 400 by to get 200? And this is what I was talking about. Some people just look at that and they'll know what it is. 1/2. But if you didn't know, then you'd go 200 over 400 and you'd get 1/2. Or you get 0.5. Decimals work fine here. Then 100 over 200. 1/2. And you go, oh, it's exponential. There's only 3 possibilities. And usually you can look at it and see if it's linear. It works all the way through 25 over 50, 1/2. 12.5 over 25, 1/2. So the first ratios are equal. This is exponential. Did one of them have to work? No. It is possible that it's none of these things. Mostly in grade 11, though, we make them one of these 3. No? I'm just going to scroll down a little bit here. Can you look at this one and know what it is? It's linear because it goes down by 4 every time. I personally don't need to subtract to see that's going down by 4 every time. But if the numbers are crazy, you might need to subtract to figure it out. But these are all the same. The first differences are equal. Right, now you're starting to see. You don't have to do it by trial and error. It is possible to look at the first couple of numbers and see what's going to happen here. See? This is multiply by 3, multiply by 3, multiply by 3, multiply by 3, multiply by 3. But maybe when you get down to here, you're like, well, I don't know that's multiply by 3. I've got to take 486 and divide it by 162 to make sure. Yeah. Absolutely. That one's exponential. This is not linear. This next one goes down by 2, down by 6. I don't need to start the first differences to know that.
It's quadratic.
He thinks it's quadratic. I'll try it. Down by 2, down by 6, down by 10, down by 14, down by 18. The differences went from -2 to -6. It went down 4, down 4, down 4, down 4. That's quadratic. Last one. It's not linear. I can tell that by looking at it. Maybe you start the quadratic thing and go down by 100, down by 20, down by 4. No, that's not going to be second differences. So now let's check the ratios. 25 over 125. What's 25 divided by 125? Someone got the calculator there? No, it's not 5. 1 over 5.
So it's just divided.
5 over 25? 1 over 5. 1 over 5? 1 over 5. 0.2 over 1 is 0.2. Uh-oh. 04 divided by 0.2 is 0.2. Is 1/5 0.2? Yeah, it is. So this is exponential. So you might have to play around with the decimals a little bit there. You have a question?
Yes. Does it matter if I write divide 2 or multiply by 1/2? Or like divide by 5 or multiply by 1/5?
Isn't that just the same thing?
It is the same thing. What we're going to find later, though, is for exponential functions, we're going to want to know what the multiplier is.
Oh.
We're going to be really curious about what's the multiplier. So to get the numbers, maybe it won't matter, but to make the equations, we'll want to know what is the multiplier.
Okay.
Yeah? So. Any questions about that? How much of this did you remember once I started doing it? Did you remember first differences once I started doing it? Did you remember second differences once I started doing it? So if you sort of remembered that, ratios is just, I'm going to do it with dividing instead. That's all. All right. More time there? Did I ask that already? More time? Yes? Well, some people are taking more time. They're going to hand out the unit homework sheets. Notice that 5.1, I gave you a different version of it. I gave you a different version of the investigation. So when you see 5.1 homework here, you don't have to do it because you're doing my version of the investigation, which I like way better than the one that's here, even though it's pretty much the same. So you'll be starting with 5.2 homework this evening.
Thank you.
Thank you, Mr. Todd. Thanks, Mr. Todd.
You are so welcome. Oh, that was close. Okay, last page. Right, am I right? You got one more little slide to go. Consider the functions y equals 2x, y equals x squared, and y equals 2 to the x. You may know the answer as soon as I say it, but I really want to make an important point about these different graphs because they all look sort of the same algebraically. 2 times x, x to the power 2, and 2 to the power of x. I've only used 2's and x's here. I want to compare those three functions. As the value of x increases from 0 to infinity, and if infinity bothers you, from 0 to really big, that's what infinity will mean for us for a while. At least till the end of advanced functions, we can get away with just thinking infinity really big, like really big, bigger than anything else in the question, off the charts huge. Which of the three functions do you think will increase the fastest or the slowest? If you did the investigation, you already know which one increases the fastest. If you haven't, that's fine. I'm going to do it here. I'm going to talk about it. I'm just going to act like I don't know. Graph these functions on the interval 0 to 6. How do the growth rates compare?
It's 2 to the exponent x.
I'm going to graph 2x.
Sounds good, Mr.
I don't know. Stay with me because I hope this doesn't mess you up what I'm about to do here. I'm not going to build a table of values. You can. I'm not putting down table of values, but it's possible that some functions are simple enough now that we can do the table of values as we're building the graph. Okay? So here in blue, y equals 2x. Table of values and a graph all at the same time in my head. You're skeptical. Don't be. Watch this. If x is 0, what's 2 times 0? If x is 1, what's 2 times 1? 2, right about there. If x is 2, what's 2 times 2? 4. If x is 3, what's 2 times 3? 6. Mr. Todd, I can't keep track of all that. You're messing me up. Well, then just build a table of values. You go over here and go x, y equals 2x, 0, 1, 2, 3, 2, 0, 2, 4, 6. Yeah, no problem. I have no issue with that. I'm just giving you the opportunity to go, maybe with simple functions I can get the graph faster. So that's 8, that's 10, that's 12. Linear, 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 linear. If it doesn't look perfectly linear, it's just because I was estimating the points. I know it goes through there. So I'll just make the points a little bigger. It was just bad estimating. What'd you say, arrow?
Yep.
There.
I was talking to Carter, but
Linear. I wondered. He called me buddy. I'm like, wow.
no, I went to call you buddy.
You can call me buddy. Y equals x squared. Can we square numbers in our head while graphing them? I don't know. We'll try it. What's 0 squared?
0.
What's 1 squared? 1. Actually lower than the other function. Maybe linear grows faster than quadratics. Oh, you should know better than that after a chapter of quadratics. What's 2 squared? 4. What's 3 squared? 9. 4 squared? 5 squared? Do you see quadratics is like out taken over, right? There's the parabola y equals x squared. Can you see that the parabola grows way faster than the linear function and is increasing its growth rate? It's taking off. Like the gap is opening and it's opening wider all the time. Maybe that's obvious. Maybe you're like, yeah, I know. I've graphed enough parabolas. I know parabolas grow a lot faster than lines. Last one. What other color do I have available?
Pink.
Black, red.
We want pink.
Oh, wait, I didn't do that in blue, did I? Let me just fix that. Blue straight line. That was supposed to be a blue straight line. So you can see. Then, will black look different? We'll see. This one I am going to do a table of values for because you might not be as familiar with this. Shh. Shh. I would never say shut up in class.
I don't.
I just want to sometimes. Like now. In case you're having trouble with the investigation, here it comes. What's 2 to the power of 0?
0.
No.
1.
1.
My bad.
It's like I'm not multiplying 2 a bunch of times. I multiplied it 0 times. I'm not multiplying by anything. Oh, I'm multiplying by 1. 2 to the 1? 2. 2 to the 2? 4. And some of you are like, I know the pattern here. Maybe I can't do them in my head, but I know I'm multiplying by 2 every time. I don't know why I wrote 15 there. That's complete random nonsense coming out of my brain. 2 to the 5? 32, 2 to the 6, 64. Here they come. 0, 1, 1, 2, 2, 4. Can't really tell the difference between these 3 functions right now. 3, 8. It's actually smaller. 4, 16. Still even with x squared. 5, 32. But do you see what starts to happen? 6, 64. See, exponential has trouble getting going, but once it does, look out. Now listen, friends. We just went through a pandemic, and we would have had a lot less trouble if people understood exponential functions better. Every time we were on lockdown, this is what happened. They went, oh, there were 16 cases in Brantford today. Next day, 32 cases. Oh, that's weird, which is not what they should have said. They should have said, it's gone exponential on us. We're in trouble. Shut it down now. But every time they waited until it went 64, 128, and then we had to shut down for months to get it back under control. The lockdowns were not a problem. The timing of the lockdowns was horrible. If the very first time we hadn't to wait until March break, if we had a shutdown on February the 15th, we might have only been out of school for a few weeks. Instead, it took months to get it back under control. Because once something goes to exponential, look what's happened. Let's talk about what the next one is. What's after 64? Let's say this was cases of coronavirus in Brantford. After 64, what's the next day going to look like? 128. Now the ER's flooded, overrun, and we could have controlled it. Look at, when it was back here, things were under control. We could have fixed it then if we just had gone to a mini lockdown then. Easy to say afterwards, after it's all happened. But this is what exponential growth is all about. Really scary growth. It's also why, let's say you're sitting beside someone in class at noon, and you hear them coughing a little bit. They're clearing their throat. I'm like, geez, I'm not feeling too good here. And by the next morning, you're already like, no, I'm not feeling too good. Because the virus gets in your body and goes, whee! Because it likes it in there. It's like, this is good. And then you're already sick the next day. Answer the questions, finish the lesson. In general, growth occurs more rapidly under exponential growth, followed by quadratic growth, then linear growth. And why does it say in general? Is because look at, if I just look up till x equals 3, I might not have noticed the difference between the two of them. It's not until time passes that you notice how crazy exponential growth is. I'll give one last fun example for you on a Wednesday. There's an old legend that may or may not be true about a traveling mathematician slash jokester who came and did some work for a king. And the king said, how would you like to be paid? And the mathematician slash jokester said, well, here's what you do. Get out a chessboard.
Don't touch me.
Shh. And on the chessboard, give me 1 penny on the first square. Then just double it on each square across the board. Let's see what happens. Let's see how much money you're owed if you start with 1 penny and double it on each square of a chessboard. How many squares are on a chessboard? 64. Okay, so I'm going to take 0.01, which is a penny, and I'm going to double it on the second square. Get the decimal. 2 pennies. Ooh. The king was very happy. I paid them 2 pennies on the second square. Then multiply that by 2. Go to decimal. Ooh, 4 pennies on the third square. Fourth square. 8 pennies. You're unimpressed. Fifth square. Oops. Times 2. 16 pennies. Not bad. 32 pennies by the sixth square. No, fifth square. Sixth square. 64 pennies. Seventh square. $1.28. Eighth square. $2.56. The king's starting to get a little worried now. $2.56 on the eighth square. We got to get to 64. Times that by 2, 8 more times. Let me just do the next row. 3, 4, 5, 6, 7, 8. By the 8th square, that 8th square is $655.36 by the 16th square. Let's do another row. 17, 18, 19, 20, 21, 22, 23, 24. $167,000. Doubling is a powerful procedure. It doesn't start off very powerful. 1 penny double, 2 pennies, ooh. 4 pennies, ooh. 8 pennies, 16 pennies, 32 pennies, 64, $1.28, and then it gets out of hand. The jokester ended up owning the kingdom, by the way, in the legend.